Hello everyone, welcome to my third video. This has been highly requested by current Chem 12 students. So let me summarize the topic of solubility equilibrium for you and hopefully help you with your test. This time I'll just do a summary of the unit instead of reteaching the whole thing. So let's get started with solubility equilibrium. First, imagine you were dumping some salt into water. What happens is the salt will dissolve into its ions, which are Na plus and Cl minus. But what happens if you keep dissolving? Eventually, you'll have what's called a saturated solution, where you can't dissolve anymore at that given temperature. So any extra salt you add will stay as a solid once it hits the saturated solution. So you have a clump of salt in the solid form. And like I mentioned in the equilibrium video, what happens here is that the ions are in equilibrium with the solid. So the solid is dissolving into its ions at the same rate that the ions are precipitating into the solid. And this is only true for saturated solutions. The term solubility refers to the maximum concentration of solute that can dissolve in a saturated solution. So in our saltwater example, the solubility would be the concentration of your ions. Now this unit includes a lot of basic stoichiometry that was covered in Chem 11, so I won't cover it here, but make sure to study that. Now, as we know, when a solid dissolves into its ions, it'll look like this, a solid and its ions, and N and M are their coefficients. And similar to how we had an equilibrium constant, this time we have a solubility constant called KSP. And before, in KEQ, this was equal to your products over your reactants. But in KSP, our reactants are solid, so they are not considered. So what we have is KSP is going to be equal to concentration of cations raised to the power of their coefficient times concentration of anions raised to the power of their coefficient. And this is basically a representation of how much solid can actually dissolve in a saturated solution at a given temperature. And same as your equilibrium constant, temperature is the only thing that affects it. Now let's try an example. It tells us to find the solubility for CuI, and we're given the KSP. And what this is asking us is, at this given temperature, in a saturated solution, what are the concentrations of the ions? We can start by writing our net ionic equation. So we have CuI, which is a solid. Make sure you check your solubility table and make sure it's a solid. And this is dissolving into Cu plus, Aq, and I minus Aq. And we're trying to find the concentration of these two right here. And how do we do that? First, we're just going to let X equal to our solubility. And because we have a 1-to-1 ratio here, we're going to say that this is also equal to our concentration of Cu plus, which is equal to our concentration of I minus. Next, we have to write our KSP expression. So it's equal to our products raised to the power of 1, and no reactants because that's a solid. And plugging in some numbers, we get 1.3 times 10 to the negative 12 is equal to x squared. And that gives us x is equal to 1.1 times 10 to the negative 6 molar. And that is our solubility. Next, let's find the solubility of AlOH3. And they give us the KSP. We'll start by writing out our net ionic equation. So I have my salt, which is a solid equilibrium with its ions. So I have Al3+, and here we have 3 hydroxide ions because we have a 3 here. Now, same as before, let's let X equal to our solubility. And here's the tricky part. So you see that we have a 1 in front of the Al3+ as a coefficient, but in front of the OH- it's a 3. So what this means is our solubility is going to be equal to concentration of Al3+, but then our concentration of OH- is actually going to be equal to 3x, because if you look at our equation, it's going to be 3 times as much as your Al3+ because of the coefficients. In other words, whenever your AlOH3 dissolves, what results is always 3 parts hydroxide and 1 part aluminum. Next, let's write our KSP expression. It's equal to our concentration of Al3+ times concentration of OH-. Make sure to raise it to the power of 3 because of the coefficient. And now let's plug in some numbers. 2.6 times 10 to the negative 39 is equal to x times 3x cubed. And doing the math, we find that X is equal to 9.9 times 10 to the negative 11 molar. And something I forgot to mention is that solubility, so X, or what we just calculated, can also be defined as the maximum amount of solid that can exist or can be added before a precipitate forms. Next, we're given the concentration of one of the ions, and we're asked to find KSP. So we can start by writing our equation. I forgot to mention in the previous example, always include your states. So these two are aqueous. But anyways, now we have to make an assumption. So it says that our concentration of lead is this much, and we have to assume that this concentration came purely from dissolving the solid and not from anything else. So if I were writing a test and I had this question, I would write that I'm assuming that this solution was made by dissolving your solid, and the ratio of Pb ions is half of that of chlorine ions. Now we write our KSP expression is equal to our products. Make sure to raise that to the power of 2. It tells us our first concentration. Our concentration of Cl- is still unknown, but we made our assumption saying that the solution was made purely by dissolving our solid. So looking at our ratio here, we know that our concentration of chlorine is going to be double of lead. So we can say it's going to be 2 times 3.56 times 10 to the negative 2, all squared. And this will give us a KSP of 1.80 times 10 to the negative 4. Now let's look at this question. It's saying that 50 milliliters of 0.040 molar of whatever this thing is called is mixed with 150 milliliters of 0.0080 molar of this other thing. And the KSP for CaSO4 is this. And it's asking if a precipitate will form. So this may look confusing at first, but what we come to notice is that these two things here, they actually dissociate 100% or close to. If we check our solubility table, they are soluble. So that means it's going to readily dissolve into its ions, and there won't be an equilibrium. So what we can say is, for our first one, CaNO3 2, it's going to go into Ca2 plus 2NO3 minus. And our second one, we have NH4 2SO4. It's going to dissolve into 2NH4 plus and SO4 2 minus. And now using basic stoichiometry, we can find our concentration of ions because we know these are one-way arrows. So I'm going to skip how to do this step because it's just Chem 11, but you should find that these are your concentrations. And the reason why I'm finding concentration for Ca2 plus and SO4 2 minus is because those are the only ions that actually matter. Because it's asking if a precipitate of CaSO4 will form. So we can ignore the NH4 plus and also your NO3 minus. Those are not significant in this question. Alright, so now we know that we have a solution and there are these two concentrations of ions. Now similar to our last unit, we can do what's called a trial KQ or trial KSP. So we're going to call it Q. And it's going to be equal to concentration of Ca2 plus times concentration of SO4 2 minus. And if we plug in our numbers, this is going to give us 6.0 times 10 to the negative 5. And now compared to our real KSP, we can see that it's smaller. So how do we raise our KSP? Well, since our KSP is only our products, so only our ions, we want to make more ions. So how do you make more ions? You get rid of your solid. You dissolve your solid to make more ions. So since we're not making solid, we're getting rid of solid, this will not precipitate. Now let's look at the common ion effect. So in this question, it's asking us for the solubility of PbI2, but this time it's in a 0.10 molar NaI solution. So the NaI is actually going to provide more I minus ions. So that's going to change our calculations a little bit. We'll start by writing our net ionic equation. And just like before, we're going to make our X equal to our solubility of our solid, which is our PbI2, which is then equal to our concentration of Pb2 plus. And our concentration of I minus is going to be 2x. Except you gotta remember that we're adding this into a 0.10 molar NaI solution. We know that NaI is soluble because Na is very soluble. And we're actually we're gonna add 0.10 molar to whatever the iodine concentration is, because it's sitting in the solution of iodine. Now we can write our KSP expression, which is equal to concentration of Pb2 plus times our I minus squared, which is equal to x times 2x plus 0.10 squared and now we can see that the math gets really bad. So what do we do in this situation? We're just going to assume that 2x is negligible, because usually solubilities are very small and it's like nothing compared to 0.10 molar. So we'll say that our concentration of I minus is approximately equal to 0.10 molar. But remember to state your assumption that 2x is very, very small. You have to write that down. So now what we have is our KSP, which is 8.5 times 10 to the negative 9, is equal to x times 0.10 squared. And solving for x, we get 8.5 times 10 to the negative 7 molar. And that's our solubility. So to summarize, the only thing that's different for the common ion effect is that you have a common ion, such as our iodine in this situation, which will be then added to our concentration over here. And then you have to assume that your x is negligible, because then the math gets ugly. And then at the end you have to check to make sure if it's actually negligible. We see that 8.5 times 10 to the negative 7, that's way smaller than 0.10. So it is negligible. And that is how we do it. So that's the harder part of this unit. The rest is pretty easy. So that was just my summary. Hopefully that made sense, and good luck on your test.